Hello students, in this video we will learn about series. So let's start. What does this term series means? So I'll start with the term which you already know the word sequence. So now if I define the sequence S1 equal to A1, S2 equal to A1 plus A2, S3 equal to A1 plus A2 plus A3 and so on, and Sn will be a1 plus a2 plus a3 till an, which you can write it as k. Okay, so you have a sequence that is an, and now you are writing like this, like you are defining s1 is equal to a1 s2 a1 plus a2 and so on. So the sequence which is formed, the sequence Sn, are called sequence of partial sums, and the nth term is called as that is Sn is called, this one is called nth partial sum. Now I'll tell you how this is related to the definition of series. So I hope this one is clear, that you have a sequence an and then you are defining essence like this. So now before defining, now just observe that if you take the limit n tending to infinity Sn, this is equal to, and this will be equal to, I made n tending to infinity so I can write this. So if you take the limit of the nth term, that is nth partial sum, you are getting this. Now this term is called, we call this an infinite series. So now it is clear that what is your infinite series. So you can write it like this: let an be the infinite sequence of real numbers, then the expression of the form this is called as infinite series. So infinite series is a sum of the infinite sequences of numbers. So this is the sum of infinite sequence of a number. So I hope the definition of infinite series is clear. Now we will discuss an important theorem. It says that if the sequence of the partial sum Sn converges, then say to limit L, then the infinite series also converges to limit L. And if the sequence of the partial sum diverges, then the infinite series also diverges. That means that you have already seen the meaning of Sn, and if you find the limit and it goes to some finite limit, some unique finite limit L, then you can say that our series is also convergent and it is going to limit L, that is its sum is this L. But if you find the limit of this partial sum, that is Sn, and it is either infinite or not defined, then this implies that the you cannot find the is divergent. You can write it is as divergent, that is you cannot find the sum of the series. Now it is important to know that there are only few series for which you can find out the sum, like you have a geometric series and telescoping series, which I'll discuss further, for which you can find out the sum. But for the other series, you can tell that whether it is convergent or divergent, but you cannot find its sum. So let's see the geometric series for which you can find the sum also. Okay, the series of the form this is called as geometric series, where a and r are the fixed real numbers and a is not equal to 1. So clearly this a is a first term and r is a common ratio. I gave this equation as this series as equation number 1, and this geometric series 1 will converge to this value a upon 1 minus r if mod of r is less than 1, and the geometric series 1 will diverge if mod of r is greater than or equal to 1. So now we are going to prove this result, that when this geometric series will converge and when it will diverge. So let's start the proof. So now we will prove this by taking cases. So my first case is case 1, when r is equal to 1. So when r is equal to 1, if you see the series 1, the nth partial, the nth partial sum of the series will be, of the series you can write series 1 will be and which will be equal to n into a. Now when you will find out the limit of this nth partial sum, you can easily see that this will go to either plus or minus infinity depending upon the sign of a. So therefore you can conclude that the series 1 diverges for r is equal to 1. Now we will make the second case, that is for r is equal to minus 1, and we will see how is the nature of our series 1. So I'll write down the case 2, that is when r is equal to minus 1. Again you will find out the partial sum of your series 1, and that will be equal to, now if you find out the limit of this, you will find this is equal to 0 when n is even, and this will be equal to a when n is odd. So this is not unique, and so the limit does not exist. So you can say that therefore the series 1 diverges for r is equal to minus 1 also. So clearly you can see that you found out the limit of the nth partial sum, and in this case it is for r is equal to 1, it is coming out to be plus minus infinity. So the sum of the series is also divergent. So this is for r is equal to 1, and when you consider r is equal to minus 1, again the limit is coming to be not unique, and therefore the limit of this does not exist, and so the series 1 will diverge for r is equal to minus 1 also. Now let us take a case 3, that is when mod of r is not equal to 1. So in this case also, when you find out the nth partial sum of the series 1, so I can write the nth partial sum of 1 as and I'll call this as equation A. Now if I multiply R with equation A, I'll get now I'll call this as equation number B. So subtracting both the equations, I'll get this. This implies that Sn is equal to A 1 minus R to the power n 1 minus R when R is not equal to 1. So if you find the limit of this, now if you find the limit of Sn for n tending to infinity, this will be equal to A 1 minus R when mod of R is less than 1, as this will go to 0 as n tends to infinity. So you find that when R is less than mod of R is less than 1, then the nth partial sum goes to this limit. So this implies that the sum of the series will be also equal to the infinite series will also converge to this value. Now let us see what will be the limit for when mod of R is greater than 1. So this will be equal to infinite, as R to the power n will go to infinite as n go to infinite when your mod of R is greater than 1. So if mod of R is greater than 1, then what you will find that your sum will be infinite or your series will be divergent. So you can write that 1 is convergent for mod of R less than 1 and 1 is divergent for mod of R greater than 1. Now all the cases are considered, so this completes the proof of the theorem. Okay, now let us take an example. So convergence or divergence of the series summation n tending n is equal to 1 to infinity, that is equal to this is your series and you have to check that whether it is convergent or divergent, and if it is convergent then find the sum. So this is your question, so let's solve this. So for this see that the summation of an is equal to which is equal to 1 by 4 minus and so on. So clearly it is a geometric series with a 1 by 4 and R is what? Minus 1 by 4. So since you have already proved that mod of R which is equal to 1 by 4 which is less than 1, this series, therefore the series is convergent. You have already proved it that the geometric series is convergent only when mod of R is less than 1, and again the sum of the series sum will be equal to a 1 minus R, which is equal to a is what? A is 1 by 4 and R is minus, so this will be equal to 1 by 5. So the answer is yes, this series is convergent and the sum will be equal to this 1 by 5. So now let us do another example. Okay, so let's do another example. So find the value of x for which the series, I'll write down the series, this is convergent, and also find the sum of the series. So now you know that that this is a geometric series. Since when you will open it, what you will get, put n is equal to 0, you will get 1, then log of x plus this, and so on. So clearly this is a geometric series. It is a geometric series, and with a is equal to 1, and what is r? R is log of x. So now you know that this will be convergent when mod of r is less than 1. This will give you the value of x. This implies that log of x should be between this value, and this implies that x should be in between this. So whenever the x is between this 1 upon exponential to this, so the your series will be convergent. And then you also need to find out the sum. So you already know that for this the sum will be equal to, which is equal to 1 upon 1 minus log of x. Now x should be in between these values. So whenever you choose any x in between, the sum of the series will be equal to this term. So now we will study about telescoping series. Now there is one another type of series for which we can find out the sum, that is called as telescoping series. So if you want to define it, these are those series whose partial sums eventually have the fixed number of terms after cancellation, and these series follow some patterns, and by using the concept of partial sum we can find its sum. So I think that this example will make more clear that what does this telescoping series mean. So let us check the convergence of the series. This is equal to, so you want to check the convergence of this series. So if I open the series, I'll have, so this is my nth term, and so on. So if you consider the nth partial sum of this series, so you can clearly see that the terms will cancel out. Like if I write the nth term, that is the sum till a1 a2 till an. So I'm writing out the nth partial sum. So clearly you can see that the terms are cancelling, that this is cancelled with this and so on. So finally what you are left with, you are left with the first and the last term. So you are left with this. Now if you put the limit, if you find the limit, this implies that this will be equal to 1, which is finite and unique. So we have already seen that if the limit of the partial sum tends to a finite value, then the series will also tend towards that limit. That is, you can find the sum of this series and the sum of the series will be equal to 1. So you can say that therefore this series converges and its sum is equal to 1. So I hope this will clear what is the telescoping series. So now we will do the next question. So if you have a series like this, suppose that you have a series, this is example 2, and you want to find out that whether this series is convergent or divergent, and if it is convergent you want to find the sum. So first of all note that if you take a1, that is the first term, I can write this as this, and if you take a2, I can write it as like this, a3, I can write this, sorry, this will be, and so on. So now if I find the nth partial sum, that is my Sn, this will be equal to a1 a2 till an. So if I write, this is my a1, this is a2 and a3 till an. So my nth term will be this. So again you can observe that it follows some kind of pattern and the terms are cancelling out. Like all the terms will be cancelled and we will be left with the first and the last term. So this implies that if we take out the limit, we are getting half. So this implies that the series, therefore the given series is convergent and its sum is equal to half. Okay, so let's do the last questions. This is my last example, that if you have a series and you want to find out whether this series is convergent or divergent. So first of all, again see that you can write out your nth term as this. That is, my first term will be, I can write my first term as this. My second term will be equal to this, and so on. So if I find the nth partial sum, what will I get? Sn, that is a1 plus a2 till an. So again I'll see that all the terms will cancel out. So let us write this. So you can see that the other terms are cancelling out, and again we will be left with the first and the last term. So my Sn will be equal to this. So when you find this, imply that if you take the limit of this Sn, this is equal to 5. Again, therefore, the series converges and its sum is 5. So now I hope that this telescoping series is clear. In the next lecture, we will be discussing about how you can say that the series is convergent or divergent, because every time we cannot find the sum of the series. There are special series like you have seen, geometric series and the telescoping series, where you are able to find the sum, but there are other series also for which you cannot find out the sum, and that we will see in the next lecture. Now, for practicing, you need to follow this book, Calculus and Analytic Geometry by Thomas and Finney, and go to section 8.3 and solve the problem exercise 8.3. Thank you.